All right, welcome back. We seem to have a reasonable return rate here, so that's pretty good. So where were we? We developed these two representations. That was an hour and a half worth of work. We have the random time change, and we have the representation for Gillespie's algorithm. And what I want to do now, so that was, it took a lot of effort. I want to show, I want to get approximations down. So we have the exact model, as we've already seen in some talks, and we'll undoubtedly see in many other talks. Sometimes what happens is you have a model where, for whatever reason, it's difficult to simulate trajectories exactly. It's not difficult. Like, you can use any of these. You'll get a trajectory if you wait long enough. But if you have to wait a minute, let's say, for a trajectory, and you want 1,000 trajectories, you're in trouble. So sometimes you want an approximation method. Okay? So I'm going to build those up. And I'm going to use the random time change representation to motivate each of these approximation methods. So we're going to talk about tau leaping. That's the numerical approximation methods. Two different SDE approximations and an ODE approximation. So I'm not going to spend much time on tau leaping, and if you paid attention, which all of you should have, to Dez's talk, you know all this already because he already showed this. But let me show you tau leaping now. This was derived first, I think, by Dan Gillespie in a paper in Journal of Chemical Physics in 2001. And essentially, it's an Euler approximation to the integral that we see in our representation. So there's our random time change representation. I'm going to do one step of tau leaping. That's what this slide is all about, one step. So tau, I'm sticking with the original notation. Tau, for tau leaping, is my time discretization step, typically h, or delta t. But now it's tau. So if I want to go from time 0 to time tau, there's the exact representation. An approximation would just be do Euler on this integral. And if you do Euler, you just set that equal to z0, right, z at time 0. So you just ask what is that intensity, multiply by tau, because that's the easiest integral in the world, and I have a unit rate Poisson process evaluated at that time. Well, that's just a Poisson random variable. That's because it's a Poisson process. I guess I didn't quite say that earlier, right? But if you have a Poisson process and you integrate up to time blah, then the number of jumps is just a Poisson random variable with that parameter. Okay, so you just generate a Poisson, one for each, I should have had a little sub k here, one for each reaction channel, multiply by zeta k, the direction you go in, sum it all up, there's one step of tau leap, repeat the process. Okay? Again, this was on Dez's slide. You can write down a representation for tau leaping, there it is. The only difference, I mean, it's literally the same notation as yesterday. All I've done, this looks exactly the same as the exact random time change representation, except I have this function, it's z of eta of s. And eta is just, it's a step function. It fixes you, you have a time discretization, and it fixes you at the left endpoint of your time discretization. That's all it does. So for example, if I was tall enough and I could put my hand over the YKs and get rid of those, that's just Euler's method for an ODE. That's all it is. Okay? And now with the YKs there, it's Euler's method for tau, for these models, so it's, and we call it tau leaping. Okay? There's the algorithm. It's very, very simple. Yes?
What happens if you put something that is instead of a step function, like maybe like a linear function or something else? Is there like an interpretation for that, or?
Say that, I don't understand the question.
So instead of using a step function, you compose it with something else like a linear function, or?
Are you talking about the YK here or the intensity function?
The intensity function.
Hold that question just for a second. I'm going to show you can do other things if you want. So yeah, that's a good question, but just I'll address it in a second. So tau leaping is this. It's initialize. I mean, if you go past your end time, reduce your time, but don't worry about that. You have your time window, and all my taus have become h's out of habit. For each reaction channel, set lambda k to be a Poisson random variable with the right intensity, then add them all up, multiplied by the reaction vector. Okay? So just Poissons, update. Poissons, update. There's more to this, of course. I'm not showing everything, right? You could go negative. There's certain things you want to account for. I'm not putting there's lots of papers out there about how to fix such issues. I'm not going to talk about those, okay? But that's the basic strategy. This is getting towards what you were asking about. So you don't have to do Euler's method if you don't want to do Euler's method. So for example, and I think this is exactly what you were asking, let's say you're in a regime where this makes sense, and you say, look, I roughly know where I'm going to be halfway through. I want to do a midpoint method, right? I roughly know where I'm going to be halfway through my time interval, right? There's where I am. So I add on 1/2 my time step times my intensity function times the reaction vector, right? Is this where you're getting at? I think, yeah. So I'm going to use that in my intensity function, right? So the only difference is now instead of using the left endpoint, I use y star. This is the estimated midpoint. I generate my Poissons with intensity lambda k of that. So again, I'm just, maybe I should have splashed this up again. I just have an integral I want to estimate. However, if I can estimate that integral well, then I get a better estimate for my stochastic process. That's all I'm doing. Okay? So I think this will give me a better estimate. This is deterministic midpoint. Update. In certain scalings, this is a good idea. In certain systems, it's not a good idea, or it doesn't help much. It rarely hurts. You can write a stochastic representation. You get pictures that look like this. Here's a silly Locke-Volterra model with 1,000 molecules to start. If you use an exact Gillespie algorithm and 30,000 samples and make a distribution, you see, you can kind of see what's going on, right? Euler tau leaping misses the mark pretty badly, or I don't know if it's bad or not, but for a certain step size, whereas midpoint does what you think. It looks like a higher order method. You can make this precise in certain scalings, but I'm not going to get into that right now. Okay, so it sometimes works. There's other things you can do. If you have a stiff system, you can use implicit methods. People are doing that here, and I can't find them here. Yes, there they are, right? So, there's a poster showing how to use implicit methods to do things for stiff systems. Anyway, so there's lots of bells and whistles that I'm not going to get into, but that's the basics of tau leaping. You have this integrated intensity function. How can you estimate that integral well? If you can do that, you have a new numerical method. Okay? It's very simple. Once you see the random time change representation, it's sort of obvious how to do it. Fine. That's all I want to say about tau leaping. We're going to come back to tau leaping tomorrow morning. So I'm going to talk about fancier like multi-level Monte Carlo methods, and you can then use tau leaping with the exact process to build really fast unbiased estimators. Okay, so that's for tomorrow morning. For now, I want to talk about different approximation methods. So I'm going to start, and to be honest, this is the part of the whole lecture series I am most worried about losing people. I'm going to talk about a certain scaling. So please ask questions. Everything, you need to know this scaling to make any sense of what I'm going to say from here on out. So I want to take a model. I want to envision large counts, hundreds, thousands, 10,000, whatever, large-ish all the way to very large counts of each molecule. And I want large rates. Now in that scaling regime, typically people say, don't worry about the stochastic model. Maybe use a Langevin approximation. Maybe use a linear noise approximation. Maybe go all the way to the reaction rate equations. So I want to show you how to make all that precise. Okay? So, oops. And I think Kit asked about this earlier, right? The volume issue, right? So you should think of V as the volume. So we imagine our system having a large parameter V. Okay? You can think of it as the volume times Avogadro's number if you want to scale to concentrations, or just think of it as 1,000. That's fine too. Okay? You have some large parameter. We assume that my initial counts are all order V, 1,000, 2,000, 1.5 thousand, 800. Okay? All roughly 1,000. Okay. Notice there's a subscript V. I'm going to have a parametrized family of models in a second. Okay? And I'm going to let V go to infinity. So I have x superscript v, that is the counts. I now divide by v, and that's x bar of v, okay? So I've scaled out to get to order 1, okay? So I'm scaling basically to get to concentrations. Is that clear? So I've divided everything by v. Okay, we can write down the random time change representation for this model. It's easy. I just divide everything by v. I divide it by v, I divide it by v, I divide it by v. What do I do here? Well, I divided by v, but I can't do that, of course, so I multiplied by v, right? So does everyone agree this is exactly the same model? I've just divided by v. Yes?
I want to ask a question that's probably particularly appropriate since we're in England. So when you say the...
I'm really curious now what this question is.
Wow.
My views on the revolution.
No. not that. So when you say V is much greater than 1, of course V is dimensional. So what do you mean V is really greater?
V is dimensional? What do you mean V is dimensional?
V is a volume, right? So what do you mean by V being large?
It's 1,000. V is 1,000.
Okay.
I just want to take V to be 1,000. I don't want to deal with that right? So V is 1,000 or 10,000. Okay. Yeah. That will. I think you'll be more satisfied in a second when the way V comes in is going to depend on which reaction. So
I guess what I'm asking is, so you're really not doing a non-dimensionalization. This is scaling.
I'm just scaling. That's right. Okay. Okay. So again, think of V as volume. So what should the rate of a reaction like this be? If you now think of as V as volume, how should the rate scale with V? So what am I doing? I have S1 molecules floating around, boop, 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 and every so often this S1 molecule becomes an S2 molecule. That has nothing to do with the size of the volume it's in, right? So the rate should be independent of V. There's no V. The rate is just some number. Now, what if I have S1 plus S2 converting to S3, let's say? Now what has to happen? An S1 molecule has to find an S2 molecule. This is an accurate description. And so the rate should scale inversely with V. Okay? Etc. If I have 3 molecules that need to come in contact, A plus B plus C, the rate should scale like V to the negative 2 times some number, kappa. Okay? In general, it looks like this. If I have a reaction where I need this many of that molecule, it should be sum of how many I have minus 1, and then take a negative. Right, but looking at examples is the best way to see this. Okay? Okay, this looks hairy. So look, maybe I should do this on the board. So I claim there's a linearity here. This is the key point that I want to get across. I have my intensity function. This is the counts. V times the scaled is the counts. I claim go all the way to the right. That is equal to V. I can pull the V out basically, times a new intensity function with my new scalar rates. And let me just do that by example. I don't think I'm going to be able to talk my way through this. So let's look at S1 goes to S2. Let's see if my claim holds up. What is the rate of that? For counts, right? For counts, it's kappa x1v. These are counts, right? So if I divide by V and multiply by V, right? I divided by V and multiplied by V. This is just V. Aha, that's deterministic mass action kinetics times V on the concentrations. Let's check another. If I have S1 plus S2 go somewhere, so now the rate is scales like V inverse. So what's the rate? I have kappa over V, that's my rate constant, times the number of X1 molecules times the number of X2 molecules. That's the rate for the reaction. Again, I divide each one by V, but if I divide by V twice, what do I have to do? I have to multiply by V twice. Sorry. You can do that. I'm left with 1V times kappa x1V x2V. Again, this you should recognize as standard mass action kinetics for the ODE with, you know, a rate constant independent of V. And you can check higher order terms. It always happens. So you get this nice linearity. The V right there comes out, pops out, and you get an order 1 term. That's the key. Questions? Comments? Okay, I'm just going to keep moving then. So this object is the random time change representation. What I just hopefully convinced you of is the same as this object. I can just pull the V out, and I get an order 1 intensity function. And so I have half an hour. Let me derive this one. Again, I think it's good to take breaks from slides. So let me derive then, let's use this fact. Let's just derive the reaction rate equations. Where do the reaction rate equations, where does the standard mass action kinetics ODE model come from? So we need just one basic fact. The supremum for any u, so fix u, the supremum so I'm looking at the scaled unit rate Poisson process. I go way out, order v in time, right? I go way out, but then I divide by v. This limits to 0 as v goes to infinity. Okay? So this is a basic fact with probability 1. Okay? Basic fact of Poisson processes. Another way to think of it, I mean, if you want to think in terms of random variables, a Poisson random variable with mean vt divided by v goes to 0. Sorry, when I subtract off the mean, that converges to 0. Okay? I don't know if I should say anything more about that. Just a fact. Okay? So let's use that fact to prove what we want to prove. So what you do, so let me make some assumptions. Let's assume, just for ease, the lambda k bars are on a bounded domain. So these are bounded intensity functions, and let's just suppose they're Lipschitz for ease. Okay? So we have, and what do? I define x of t, little x of t, to be the solution to this. Okay? Little x of t is the solution to that ODE, right? Integrated ODE. So this is just, I've just written down the standard reaction rate equations. Okay? Okay? So now, let's actually look at the difference between these objects. So what's the difference between my stochastic process and my ODE? Well, you can just, you just write it down. There's the stochastic process, and I'm going to subtract off the ODE. So the way I'm going to do that, I'm going to use a triangle inequality to break up some pieces. Oops. Let me just write it down, then I will explain. I think I got it all. So as with every good proof, I've done nothing. X of t, right? X of t is just there. There's the ODE. I switched up my minuses, whatever. Right, there's x of t, and I've subtracted off the stochastic process. Now you may say, but wait, what's that? That's the stochastic, right? That's that term up there. So it's really that minus that. All I've done is add and subtract this term, and then use the triangle inequality. Okay, so I added and subtracted this, broke it apart with the triangle inequality. Right, very simple. Fine. I'm assuming everything here is I should have had a ZK. I'm assuming everything is nice in Lipschitz, so I'll use that there. This is less than c. Okay, so that term is just bounded by the integral of the difference. What's this term bounded by? I'm just going to call it epsilon superscript v, maybe, of t. What's that term? Well, look. This integral right here, I'm telling you, we assume this is bounded. So this whole integral is less than some b of t, just some number. I don't know what it is. 252, right? I've scaled v, I've gone out that far, divided by v, and I've subtracted off the mean. That's exactly this basic fact about Poisson processes, which, again, you can prove simple analysis, right? That term goes to 0 as v goes to infinity. So this whole term falls exactly into that category, and you just get an epsilon superscript v. At the end of the day, what do you have? This is less than, I can pull that in, the integral of the absolute value of itself plus some term going to 0. So who's taking analysis? What's the magic words to finish this proof? How can you basically then say, therefore, this term goes to 0 almost surely? Anyone? Looking for interaction. Magic term finishes about 87.2% of all proofs in this sense. Now, Gronwall's inequality, everyone yells. Okay. Okay, I should leave one exercise. There's the exercise for the graduate students. Use Gronwall's inequality to finish the proof that the supremum of the difference goes to 0, okay? I mean, this basically fits Gronwall's inequality. So with probability 1, we have that the supremum of the difference goes to 0. This tells you the ODE is a good approximation. That's exactly what this says. For large enough V, the ODE looks a lot like the stochastic model. If you don't believe math, you should believe pictures. So here's a model that I've scaled, very simple model. Right? A plus B equals to 2B with the proper scaling. I start with 3V of A and V of B. Think of V as 1,000 or whatever, right? And then I've divided by V to go to order 1. Here's the ODE model. I'm just going to give you simulation plots of that guy against that guy for different values of V, okay? So we start with V equals 1. Far from the limit. Shouldn't look good. And it doesn't look good, right? You have bouncing all around. It doesn't, I mean, it looks better than it maybe should. Here's another realization. The B's go extinct, right? It looks nothing like the ODE. Does everyone understand what I'm doing? I'm plotting, I simulate the stochastic model, but then I divide by V. I scale it to get to order 1 again, right? So when I take V equals 10, I actually have 40 molecules, right? 30 of A and 10 of B to start with. Simulate it, divide by 10, and put it against the ODE. Okay? It looks like it's fluctuating around it. V equals 50 looks better. V equals 100 looks better. V equals 1,000 looks really good. Okay? So there's the theorem in action. Remember, these are just single realizations. That proof showed that with probability 1, the stochastic model, scaled stochastic model, converges to the ODE, and this sort of shows it. Okay? So that's the ODE. Questions about that? Gronwall's inequality is all it is. Gronwall's inequality with the random time change representation. I don't know how to do this proof for this particular type of proof using the stochastic representation for Gillespie's algorithm. I think that's harder. No questions? I feel like I'm flying all of a sudden. Okay. That's fine. If you want an ODE, that's the ODE you use in that scaling. What about if you want to still capture some fluctuations? So let's look at the chemical Langevin equation. Oops. So what we essentially showed right over there is the law of large numbers says that if you scale a Poisson random variable by V, the parameter by V, but then divide by V, it's approximately equal to U, right? So if you have Y of V of U, it's approximately equal to U, the mean, okay? The functional central limit theorem gives you the next order correction on this approximation. And it says that a properly scaled Poisson process looks like its mean, right? That's just the mean of this guy, plus a Brownian motion scaled by 1 over square root of V. Okay? So that's the central limit theorem, which I'm not going to do anything with. I mean, I'm not going to prove it, just that's the central limit theorem. And that instantly implies the diffusion approximation for us, because let's go through this. What do we have? We have, here's the scaled random time change representation. Look, it fits this exactly, right? I have 1 over V, Y of some big V times something, right? My something happens to be an integral. I don't care. It's still something. This implies that this term should be well approximated by, if I just pull out the integral, right? That's playing the role of U up there, plus a Brownian motion evaluated at this scaled intensity function. Does that make sense? So I'm just instead of having a Poisson process, I just want a Brownian motion. And you can justify this by the central limit theorem, functional central limit theorem. This is not how most people write. Oh, sorry, I should then say, yeah. So this is not how most people write their stochastic integrals. Typically, people write it as an Ito integral. So if you have a Brownian motion evaluated at an integrated function at this time, it's distributionally equivalent to an Ito integral, so dw, but you have to integrate the square root of that function. And again, I don't know how much detail to give. You can always remember this. Just think of it this way, right? So if I have w, right? Oh, what is this? This is a Brownian motion evaluated at some time. This is just a normal random variable with mean 0, variance, whatever that time is. That's just what that is, right? And likewise, how do I get that same distribution? If I tried this, my Ito integral, this has the wrong variance, right? So you take the square root, and this is a normal random variable with mean 0, and the variance is the integral of the square of the integrand, which works out perfectly. Okay, again, maybe too much detail, but the point is, this is how most people write the chemical Langevin approximation. And kind of running short on time, so maybe I won't talk much more about it. But the key point here is note the scaling of 1 over square root of v. The fluctuations are of order 1 over square root of v.
Good question. So the reason you know it gives you Ito is because of the martingale property, right?
Yeah. There's there's a lot of devils in details here. So for example, what I actually wrote down, I don't really want to get into this too much. It's not a well-defined model, so I'm trying to breeze through this, right? So for example, intensities can't go negative, right? If they go negative, this whole thing breaks down because now I'm integrating backwards in time. So you have to be really careful, and I don't want to do that. So let me just ignore that. Other questions? This is supposed to be, just an idea of where these, what I'm saying is you can't do this, okay? So be careful. So you're right. So its suggested approximation is this, but you can't actually do this because if things go negative, this makes no sense. Bad things happen. So maybe you could put absolute value signs here, but you have to do something to make this process well defined. But I don't want to get into that. Okay. I was going to do it on the board. I don't think I have time. So does anybody want to? I always word it how I want the answer. Does anyone want to see the diffusion approximation for a model? No one? Okay. So let me do another approximation. And I'm going to draw a very silly picture, how I view these things. Okay. So here's how I view them in my head. So down at this end, we have the jump model. Okay? Up at this end, we have the ODE. So this is V, I don't know what that means, V going to infinity. I go from the jump model to the ODE. Okay? What did we just do for the diffusion approximation? For the diffusion approximation, I started with the jump model, and I made a perturbation to a new model, Z, whatever. I can't spell diffusion all of a sudden. 1S or 2? My mind just went blank. Right, so I started with the jump model, and then went to a diffusion model. I just changed the Poisson process to a Brownian motion. The linear noise approximation, sort of morally, is the opposite. I start with the ODE, and I get a new process. I'm probably going to call it Z also. Z, can't use D, can't use W. D, whatever. Okay, I get a new approximation, but I want to stress I'm going to start with the ODE and then come towards the jump model. And let me show you what I mean by that. So what you do, I assume I have little x of t, the solution to the associated ODE that I derived over there. And I'm going to let f be this function, the sum of the intensity, just for ease. Now, what do we know? We know the stochastic model and the ODE model are very close together. That's what that proved. The question is how close? So if I take the difference of them, that should be small. Right? Is everyone with me on that? right? That's what we proved. They go to 0. The difference goes to 0. Okay, it turns out the difference scales like 1 over square root of v. Okay, so the difference, d for difference, is roughly 1 over square root of v. So if I want to see what d actually looks like, the first thing I have to do is multiply by square root of v. Right, that will make it bigger. I scale up, and now it's order 1, and I can actually see what's going on. So that's what we do. We take the difference and multiply by v. Now again, I want to stress, we started with the ODE, right, at little x of t, and now I'm looking at the fluctuations of the process around the ODE. The fluctuations are order 1 over square root of v, so I multiply by 1 over square root of v. And now I want to see if I can prove a theorem. Okay, so there it is, L. The difference should have been D. It's L, okay? The scaled difference. Okay, all I've done nothing. I've just written down what, like x is this, and little x satisfies that ODE. I've just written down what they are. That's all this is. Again, I'm playing the same games here. I add and subtract a certain term. I add and subtract that term right there. And I move the square root of v in. I mean, it's hard to parse this. No one can really parse this real time. I mean, later tonight, when you're looking at this again and thinking about it, you can track all the v's. It all works out, okay? Like you have square root of v divided by v, that gives you 1 over square root of v. It all works out, okay? The point, however, there is a point, is look, that looks like a Brownian motion again. That is just L, right? I'm integrating L again. Well, once I take a Taylor approximation. So let's do that. There's my Brownian motion, and I take a Taylor approximation, and I get that term there. Right? Notice the square root of v is helpful here. I take a Taylor approximation, I get the derivative of f times L again, because I get square root of v times the difference, which is exactly what I want. As v goes to infinity, this becomes precise. LV converges in the distribution to this process L satisfying this SDE. Usually people write it as an Ito SDE, but it doesn't matter. Yeah, there it is. There's the Ito SDE version. That's L. That is the fluctuations, okay? That's not the process. That's the fluctuations, okay? Oh, and I have to. So Pete, because you asked, this is well defined because I'm integrating against Brownian motion, but the integrand is the solution to the ODE, which is always positive, or at least non-negative, okay? So this is fine. This integral makes sense, no problems whatsoever. There's a proper there's a limit theorem behind it. It's good. So what does this mean? Let me just draw this again, right? We had L was square root of v. Hold on, why am I being this cluttered? I want to unwind this now. What did we have? We had L of v was this squared difference. The fluctuations around my ODE. Now, the theorem says this is approximately equal to L, which is the solution to this SDE, which you can just solve, right? Again, if you have the ODE, you can solve this. Now just unwind this. This says, I'm literally just doing algebra here. So this is equal to, or approximately equal to, my ODE plus the solution to that SDE. That's what this says. That it's a good approximation. Okay? Is that clear? So you looked at the scale difference, prove a theorem about what that looks like, and then that's your fluctuation. So again, it's saying the stochastic model looks like your ODE plus this perturbation. Okay?
Hey, what's x hat? Sorry, I got lost.
Where?
X bar VT approximates. What's x hat?
That. I'm defining this.
Yeah,
It's there's too much notation on the slide is what it is. I should have just said this is equal to that. Yeah. Yeah, it's not x bar anymore. You gotta be careful, it's x hat now. Okay, so the point is the noise again scales like 1 over square root of e. Okay? So that's the linear noise approximation. No. I was going to derive the linear. No. If you want to see me derive either a diffusion approximation or a linear noise approximation, you can catch me at some coffee time and we can work it out together, but I don't want to do it. And that means I'm done. So I'm really being lazy by saying I don't want to do it. But I'm going to stick to my guns because I don't want to do it.
You can maybe comment on which is better.
Yeah, that's a good point. From what I understand, neither is better than the other. That there is a theorem to back this up by Tom Kurtz, of course. And apparently there used to be big fights about this. But so these were derived a long time ago. I shouldn't say that, the 70s. And you know, there was a group that thought the diffusion approximation was better. You know, groups that think the linear noise approximation is better. And essentially what was proven is that the two approximations are closer to themselves than they are to the underlying jump model. Does that make sense? So they're equally as good in a specific setting that I don't really know. I mean, this setting, this scaling. Yeah, so.
But you can derive the LNA as a linearization of the CLE, which kind of suggests that the CLE ought to dominate in some sense.
You can derive the linear noise approximation from the chemical Langevin approximation?
In some sense.
How? Like looking at generators and...
You just subtract off the ODE and look at what's left and do a linear Gaussian approximation.
I mean, that's what we did, though.
Well, I know, right.
Oh.
But in some sense, you're kind of deriving that from the CLE at some level.
Okay, I don't know. I mean, my understanding... I mean, have you seen that in practice? Actually, that's a good question. Have you seen in practice that one is better than the other?
Yeah, in cases where the mean of the stochastic process is not well approximated by the ODE, the CLE is much better. Right?
Okay.
Linear noise
I believe that, because the ODE is garbage at that point.
Exactly. So the linear noise approximation is then tracking around the ODE, which is
only because now we're just having a personal conversation. Let me. I think this is what you're saying, right? And I agree with you 100%. If the ODE model looks like this, and the stochastic model looks like this, which happens every so often, is this what you're talking about? Right? Just something terrible. Yeah. Then the linear noise approximation, I agree with you, will be just awful.
So, for example, the Locker-Volterra model, right, goes extinct, so the expected value goes to 0, right, whereas the ODE model oscillates forever. So the linear noise approximation is terrible, but the CLE is okay.
That's a good point. Okay, good. Okay, yeah.
So, I mean, I saw this type of scaling involved in error analysis a lot. But in simulation, for example, there is like classification. I mean, these kind of systems, it's better to use diffusion or to use jump models. I mean, there is this type of classification in simulation or not?
Well, I mean, this is what Des was talking about yesterday. So, in this particular scaling that I've set up, so let me be very clear about that. So in the classical scaling, that's what we studied. You know, what's the complexity for using multi-level tau leaping? What's the complexity for using a SDE approximation? And, you know, again, what we concluded is up to a log term, the complexity for unbiased MLMC, multi-level Monte Carlo, on tau leaping is always not always, I should be a little careful here. Most of the time beneficial. Did that answer your question?
Yeah, maybe.
I mean, there was never, am I wrong, Des? Is there a regime?
We're assuming that the jump model is exact, so
yeah.
We're not doing modeling comparison, we're just assuming that's what we want, and how do we approximate it efficiently?
Yeah.
Maybe that's a different question that we're looking at.
Maybe. Anyway, okay. We can talk after, because I'm tired. So, this is part 3 for tomorrow. So part 3, I'm going to, you know, so we use the representation to do, to derive these commonly used approximation methods. So part 3 tomorrow morning is going to be how can you use these representations to do fancy Monte Carlo stuff? So how can you get a good coupling for multi-level Monte Carlo? So that's for computing expectations. And then if I have time, I'll do some stuff on how to use coupling for these for computing sensitivities. So derivatives of expectations with respect to parameter values. But I think that's plenty for now, and Darren can take over. That's it. Oh, this is questions. Sorry. I'm just declaring myself done. Any other questions? No. Good.